Um, cool. So this talk is going to be about FastParse, which is a parser combinator library I wrote. If any of you want to follow along online, the slides are online at tinyurl.com/fastparse. The agenda for today, we'll spend some minutes talking about parsing text, some minutes talking about FastParse, go a bit more into the internals and other details about it, and then we'll spend some time live coding, and I'll leave 10 minutes for questions. So my name is Haoyi, and I'm currently on the Dropbox developer tools team. Previously, I was on Dropbox web infrastructure. And in my open source work, I've done a bunch of things with Scala.js and with Ammonite. But today's talk is going to be none of those. Today's talk is going to be about parsing text. So if you are a developer and someone gives you a text file and tells you, hey, there's important data in this text file, these are the tools that you typically have to deal with it, starting from the most convenient but least flexible, string split and string replace, to the most heavy-duty but most flexible, Lex, YACC, or ANTLR. So the ones on top are really convenient, but don't really work once you get past something like a file with one string per line. If you have a file with comma separated and you need to escape commas, this will not work. It's too much. For that, you can use regexes, but regexes don't really work for anything recursive. Common recursive things include things like math or JSON or YAML or any of these very common formats which are recursive. So that doesn't work. So if you can't use regex, you'll fall back to a hand-rolled recursive descent parser. So that looks something like this. This is an example from the Scala compiler. You basically have a bunch of methods. Every method returns some data structure and parses some string that is usually a member of the object that all these methods are part of. So enumerators will try to parse the first enumerator, have a while loop, keep checking things, next token, parse the next enumerator, convert the thing to a list, parsing each enumerator, you'll check the token, you'll check whether it's the first token, you'll call other methods, and these methods will go on and call other methods, each of which will parse a particular section of text. So these are very common. And in fact, it's so common that these are things that people ask you if you go for a programming interview. Hey, interview candidate, write me a parser for some kind of math expression. And you have to do it in 40 minutes. And people like it because it's tedious, it's repetitive, and it's very error prone. So it gives them lots of things to ding during the interview debrief later. So Scala uses a hand-rolled recursive descent parser. The other thing that people tend to use to write parsers is Lex and ANTLR, or YACC, and there are other tools that are similar, Bison, JSON. These are things which are used by IntelliJ, by the Python interpreter, by the Ruby interpreter. You basically write your grammar in some kind of abstract syntax, and then that generates a parser in like C code or Java code, which you then can that can compile to get a parser object of some sort or parser method, which you then can run at runtime. So this generates very fast parsers, but it's kind of complex and confusing. First, because you need a multi-stage compilation process. I'm no longer compiling my parser, I'm compiling the thing that will compile into my parser. And as a result, is complex. And so for example, this is an example from the Ruby YACC file. And you can see that apart from the pretty elegant grammar definitions up here, you have these mixed in really naughty imperative C code, as well as these things that look like comments, but I'm quite sure are not actually comments because if you take them out, the parser will break. And it's the same on the right. So you have a nice grammar definition with a bunch of pretty icky imperative code with a bunch of magic variables, which I'm quite sure are macros, in order to be compiled into a parser, which will then be compiled into something you can call. So some of you, if you have similar thoughts as me, may ask, why do people use parser generators instead of configurable parsers? I mean, I don't have a web app generator to write my web app, unless I'm using Ruby on Rails, but people here probably won't be. I won't have a type checker generator to write my type checker code. I won't have a matrix math generator to write my matrix code. I have a matrix library, or I have a type checker maybe in the library, or I have a web app framework. So why do people writing parsers tend to use parser generators? And the answer is that you don't really need to have parser generators. So this is something I discovered a few years ago. If I want to parse some math, I just import Scala util parsing.combinator.all, extend this weird trait, and then I can immediately start defining what looks like a grammar in Scala code. similar things can be done in F# or Haskell or other languages. So plus is a string plus. A number is a repeated, I'm using a regex here, but a repeated digit from 0 to 9. And an expression is a number followed by plus followed by number. And that's it. This is your parser. I can immediately call .parse all on a string and get some useful result. Or I can call .parse all on an invalid string and get an error, which is exactly what you want. No need for a complex regex, no need for a while loops and many function calls. You define a grammar, and you're done. Another thing that's nice about this is that the parsers are all statically typed. So I know that plus parses a string. I know that num parses a list of strings. I know that expression gives parsers a list of strings followed by string followed by list of strings. I can't screw that up. You can transform the parsers very easily. So let's say I don't want this weird syntax tree structure. I want the number which is the result of the expression. I simply say, well, instead of parsing a list of strings, I'm going to make the strings into one big string, and then convert it to an integer. And instead of parsing this weird list followed by after I convert this to integer, this will be parsed an integer. So instead of parsing an integer followed by a string followed by an integer, I'm going to map it, ignore the string in the middle, because I don't care what the plus parses. It's always going to parse a plus. And take the left and the right integers and add them. And that's all you need in order to parse actual numbers, to evaluate the actual arithmetic while you're parsing the numbers. So that's great. And what's even better is the fact that it's totally trivial to make your parsers recursive. So I just need to define another rule and have these two rules recursively depend on each other. So an expression is a side. You could use a better name. I'm just calling it a side. A side followed by a plus followed by a side, and I add it up, same as just now. A side is either parens with expression in the middle, or it is a number. And that makes perfect sense. And suddenly, you have a completely correct, completely recursive math evaluator in 4 lines of code. So next time someone asks you to do this during an interview, you should totally whip out Parser combinators and finish the interview in like 5 minutes and spend the other 45 minutes chatting. So that's great. And Parser combinators are great. But they have their problems, which is why people don't actually use them. Chief among the problems, in my opinion, is the performance, which, if you look at, this is a benchmark for parsing JSON using Jackson, which is a common Java library, using Spray JSON, which is a common Scala library, and using scala-parser-combinators. And something which would take 1 second to parse using Jackson would take 5 minutes to parse using scala-parser-combinators. So as much as you say performance doesn't matter, 1 second to 5 minutes does matter. In that I can click on the button and wait 1 second. If you make me click on the button and wait 5 minutes, I'll be really unhappy. And similarly, if I click on the button and it waits 1 minute, that's fine. But if I click on the button and you make me wait 5 hours, I will be extremely unhappy. So this isn't a 300% slowdown. This is a 300 times slowdown, or 30,000% slowdown in exchange for getting very nice syntax to write the parser in. So there's another parser combinator library out there, which in the Scala community called Parboil 2. And it's meant to be very fast. I think it's used in akka HTTP, akka streams, and other things. So it is used in the real world, and it's fast enough, not 300 times slower than a hand-rolled parser. But it has problems. How fast is fast? How fast is fast? Well, it turns out that Parboil 2 is within a factor of 3 or 4 of the fastest hand-rolled JSON parsers you can find on the market in Scala and Java. So if something takes 1 second using a hand-rolled 1,500-line imperative parser full of while loops and mutable variables everywhere, using a 50-line or 40-line Parboil parser, it would take 3 seconds instead of 1 second. And maybe that's OK in exchange for saving like 20x your verbosity in writing the parser. And that means if you want to parse something, you can do it quickly without having to spend weeks carefully crafting this huge 1,000-line code base. But what are the other problems with Parboil that I hinted at? One problem with Parboil, in my opinion, which is the biggest one, is the error messages. This is an error message that Parboil 2 tends to give you. And the thing is, Parboil 2 doesn't just give you this. It gives you 8 pages of this when you make a mistake. So this is equivalent to Parboil 2 saying, you are wrong. And they're not telling you anything after that, because there's no way you can figure out what went wrong with this error message. And if I tell you what did go wrong, it is I got the number of parameters wrong in my lambda. Maybe I shouldn't have gotten it wrong, but Parboil 2 also could have just told me that rather than spitting out 15 kilobytes of text at me. So if we add this to our existing tool set, we have all the old school things that people have known since 1965. And then you have scala-parser-combinators, super convenient, super fast to write, and flexible, but very, very, very slow, 300x, 30,000% slower. You have Parboil 2, which is fast, one-third the speed, 3x slower, maybe okay, still pretty fast, very flexible, but gives you crazy error messages. And the API is such that you will find these error messages. Trust me, you will not be able to avoid it no matter how hard you read the documentation. It will explode in your face. So into this crowded market steps FastParse. FastParse, at its core, looks like this. A parser, which is parameterized, a parser of a type T has a method parse, which takes an input string and an index to start at. You can start somewhere halfway through the string. It returns a result when you parse something, which is either a successful parse with a value and the index at which it succeeded. You can parse a partial parse. So for example, you can parse the first 20 characters of a string without having to go all the way. And it can return a failure, which tells you the last parser which failed. For example, maybe it failed to parse an expression. Maybe it failed to parse a close paren. And the index at which that last parser was tried and failed. So this is a very simplified overview, but to give you a feel of what FastParse is like. You have a parser, you call parse, you get something which can either be success or failure. That's it from the outside. How do you use FastParse? Use FastParse like this. This looks very similar to what you saw earlier with the parser combinators. Differences, I don't need to extend anything here. That's convenient, I guess. The import is different. That's no big deal. I had to wrap all the parsers in this weird P thing, which P stands for parser. But since you're going to be wrapping everything in parser, 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 I just called it P. And some things are called differently. Instead of using a regex, I have this thing called char in and passing a sequence of characters. Instead of repeat parser, I have parser.repeat, which is the same. You have this weird dot exclamation mark operator, which is what you use to capture a string, because you don't care about most strings in your parsing. So instead of having to manually ignore the strings you don't care about, which are going to be many of them, like every paren, every comma, every plus you don't care about, with FastParse, I asked you to annotate the parsers you do care about with an exclamation mark. Map is the same. This looks exactly the same. This looks the same. Instead of mapping and ignoring the middle plus, I just have a tuple because the plus is ignored by default unless I use exclamation mark to capture it. So there's some details which are different, but overall it looks about the same. 4 lines, you get a nice recursive math parser, and you can parse things and it works, including recursive things, and you can parse bad things and it will fail. So that's what FastParse looks like. Again, all the parsers are typed, and these is a set of operators that FastParse gives you. So it's not a tiny set, but it's maybe OK. So the basic ones are all on the left. A string can be used to parse anything. It returns unit because you probably don't care about most things you're parsing unless you use dot exclamation mark, in which case it returns the parser will provide a string, which is the thing that was parsed. Tilde between 2 parsers will give you a parser that parses one after the other, and will then give you return a tuple of both values. So this is not quite so simple. If the thing on the left is a tuple, it'll be a bigger tuple and a bigger tuple, but it's close enough. It just gives you a tuple of the values that you care about. A or B will try A, and then it'll attempt B after that, and it'll return something which is the common superclass of A and B. So if A returns a vector, B returns a list, A or B will a parser that returns a sequence, for example. Cut is same as sequence, except I'll go into more details later about why it's different. Repeat makes sense. If it returns an A, it now returns a sequence. Optional returns an option. You have look ahead, positive and negative, just like regexes. You have all the same map, flat map, and filter. So if I have a parser that returns a string, I map it to an integer, and I have a parser that returns an integer. And these are similar to what you see on collections. And you have a few like predicates, which are generally useful, like I want to parse some character satisfying a function. I want to parse some character in a list of characters. I want to parse a string in some set of strings without having to manually do like A or B or C or D or E or F. You just have put the list of strings into string in, and it'll parse any of them. So how does FastParse compare about performance? Well, FastParse's performance is within a hair, for a JSON parser, within a hair of Parboil 2's performance. So again, about 3 to 4 times slower than a hand-rolled recursive descent parser, but 85x faster. Yes, that's correct. 85x faster than scala-parser-combinators. So performance is OK. It's not as fast as Jackson, but it is not terrible. It will not take you 5 minutes instead of 1 second. It'll take 3 to 4 seconds. Another parser benchmarked is the Scala parser written using FastParse. And it's about 11x slower than Scala compiler's fast hand-rolled recursive descent parser. So this is about as fast as you can expect in Scala, probably. And this is about as slow as you can expect FastParse to perform in comparison. As the grammars get more complex, FastParse performs worse compared to a hand-rolled parser. And there aren't that many grammars which are more complex in the Scala language grammar. So this is about the worst case you can find, like 700 lines of parser combinator code versus 7,000 lines of very fast recursive descent code. So why can FastParse be 85 times faster than scala-parser-combinators, even though it looks exactly the same from the outside? And the answer is that the outside is not all that matters. The inside also matters. And so if you look at what's inside scala-parser-combinators, for example, this is a cut operator, which I still haven't explained, but I'll explain soon. But it basically parses a thing on the left, followed by a thing on the right. And if the thing on the right then fails, it won't backtrack. But we'll go into more details later. So you have this once parser thing, which takes a lambda. You have this really elegant monadic, like this bound to A, P passed into this commit thing, with P itself is this lambda, or by name parameter, which gets wrapped in lambda, gets bound to a B, and then returns this new tilde thing, which has A and B inside, and then I name it. Very elegant, very FP, very monadic, very slow. So let's look at why it's slow. Here I'm allocating an object with 2 fields. At minimum, I'm passing in A and B, it's probably going to have 2 fields. I didn't actually check, but probably has 2 fields. Here I'm allocating a lambda which captures 2 things, 2 variables in the enclosing scope, P and this. So when you allocate a lambda which captures things, it allocates the object with these 2 things as fields and initializes and puts them on the object. Here I'm allocating another lambda with 3 things in scope, object with 3 fields. Here I'm calling commit, which takes a P and presumably returns something that's not P. Otherwise, why would I call it? And because it's all nicely pure functional, this must return something else. So it's an object with at least 1 more field. Here, commit itself is a by name parameter. So the parameter gets wrapped again in a lambda. And so that's another allocation with at least 1 field. And all this happens for every character you parse. So for example, if I want to parse a Unicode escape, it would be / followed by U, followed by digit, followed by digit, followed by digit. I think followed by 1 more digit. Every character you parse, every 2 bytes or 16 bits of text you parse will need to allocate 1, 2, 3, 4, 5 objects. I believe the Java object overhead is 12 bytes per object. So that's 60 bytes of object header plus 32 bytes, 4 bytes per field. So that's 2, 6, 5, 6. I think this is 7, 9. So that's another 36 bytes in the fields of these objects. So you're allocating about 100 bytes every time you parse a single character. And then you wonder why it's slow. Very functional. So what does FastParse's internals look like? FastParse's internals do not look functional at all. In fact, they look really gross and ugly. So here you have a whole bunch of pattern matches with a whole bunch of these mutable things, which are kind of just to remind you how ugly it is to be mutable. You have these methods which you call with tons and tons of parameters. You have a bunch of if statement that's going so far it's sticking off the line onto the next line. You have a bunch of ORs and other more pattern matches and more functions method calls. But this has some very nice properties. For one, there are no lambdas on this page. Everything fits in a single method. It's not a tiny method, but it's not a huge method either. Compared to the methods you find in Java libraries, this is not that much bytecode. It's a moderately sized method. Secondly, this performs 0 allocations in the case that tracing is off. Not 1, not 2, 0, and I've run with JProfiler to make sure of that. So for example, I would allocate a list here, but if you don't tell me to trace things, I will not allocate anything. I would allocate a bigger list here, but if left-hand side is nil and right-hand side is nil, it will return nil and will not allocate anything. So 0 allocations versus 100 bytes of allocations per character you parse is probably the bulk of the reason why FastParse is 85x faster than scala-parser-combinators. The internals are much, much, much faster, even though the externals look almost exactly the same. Let's talk a bit about error handling, because that's what you do a lot when you're parsing things. So here, this is the same parser I showed you earlier. Here, I'm trying to parse some gibberish syntax, which looks almost correct, except it has this x here. And this syntax has no x in it, so that should fail. And this is saying that, well, I was trying to parse a paren, followed by expression, followed by close paren, or a number at index 0. Instead, you gave me this. Why doesn't it tell me it couldn't parse the x? And the answer is that FastParse has a pretty, following scala-parser-combinators, has a pretty dumb but very predictable mode of operation. It tries the thing on the left as far as possible, and if it finishes and returns whatever it was meant to parse. If it fails, it backtracks out and tries the thing on the right. So in this case, when I'm already in here, it will try to parse the open paren. It will then parse an expression, which will then parse the numbers, and it will parse 2 plus 3 overall. It will then attempt to parse a closed paren, which will then fail because it will find the x. Like, what's this x? I want a closed paren. And then what will it do? Well, it doesn't know that number can't start with the open paren 2 plus 3. Like, you or I may know that number cannot start with open paren 2 plus 3, but FastParse is not smart enough to know that. And therefore, FastParse will back out of this guy, come to this side, try it. Obviously, it'll fail because it wants a character from 0 to 9. It finds a open paren. And then it'll back out of both of these fellas, and then it'll tell you, well, both of them failed. I don't know which one you wanted, but both of them failed, and here's the index at which it failed. And similarly, because this thing failed, they'll back out of this thing and end up back at 0. So that's not very useful. And if only you could tell FastParse when not to back out. Like, I know we've crossed the open paren. It can definitely not be a number. You don't know, but I know. And the way you tell FastParse that is with a cut. After you cross the cut, no backing out. You are committed. You will keep going, and if you fail, the error must be somewhere after the cut. And you just add this cut after open paren, and FastParse is able to tell you, well, I was expecting a closed paren at index 7. You gave me x close plus 4. And that's actually a perfect error message. That's perfectly precise. And there was no code in this parser which is meant to do error handling except for the cut to make sure that FastParse doesn't back out too much. And it's not even magic. Like, you can follow FastParse going in here, going here, failing, coming back, being unable to back out, and then giving you an error message. It's totally predictable, which is great. Earlier, I showed you how FastParse had a very simple data structure, and in reality, it's slightly more complicated than that. In particular, in the case for error handling. So this is what it actually looks like. And the most interesting thing, apart from the fact that we have the input, we have the index, we have some random trace data, which we might not care about, is that you have this lazy trace failure object, which basically, if you ask for it, will run the same parse using the same parser, which I happen to store over here, starting at the same index, which I happen to store over here, with the same input, but with additional instrumentation to tell you later more about what went wrong. This costs something. It's not free. It costs, I think, 2 or 3 times as much as the original parse, so the total cost is 3 or 4x as much as the original failed parse. But even to debug it, or you want to help your user debug it, this could be useful. So let's see what this 2 or 3x slowdown gives you. If I'm parsing the same thing, here I know it's going to be a failure, so I'm just going to cast it. I can ask for the trace of the traced failure. Maybe not a very good name, but whatever. So if I say fail.trace, it will tell me that I was trying to parse an expression at index 0, which caused me to try and parse aside at index 0, which caused me to try and parse an expression at index 1, which caused me to try and parse aside at index 3, which is here, I believe, which caused me to try and parse either a closed paren or a character from 0 to 9 at index 7, and you gave me an x. So this is very detailed, and this actually helps quite a lot. It's not just I failed at index 7 or I failed at index 7, you are wrong. It's I failed at index 7 because I tried this at index 3, because I tried this at index 1, because I tried this at index 0, and these are the things that could have succeeded, but you gave me this. And all of this is entirely for free. I did not write any of that error handling or error reporting code here. All that's handled by FastParse. You just tell FastParse what the grammar looks like, and FastParse, if you ask for it, gives you very nice error reports. So trace gives you a string because that's often what you want, just to print it out and see what the hell is going on. But it does not hide from you the structured data of what actually was failing. So if you want to do more interesting things with it, for example, you want to inspect which frames have certain parsers in or which indexes something failed at, you don't need to like parse it out from the error message. You have this structured list of frames which you can get from it. And you have, of course, a 7 and the paren available without asking for traced, which is what is shown by default in the default error message. So apart from that, you have trace.trace parsers, which is what gives you this thing here in the original trace error message. In that, the last thing that FastParse tried to parse was a closed paren. But earlier in the parsing, it tried a character in 0 to 9 at the same index, and that failed. And so if you turn on tracing, FastParse will remember that at the cost of some performance, and will tell you that later. And it's actually correct. Like if you look at this character x, this x could have been a closed paren, or this x could have been a number from 0 to 9. And that's totally correct. And FastParse knows it. You don't need to tell it that. And it's done in a very predictable way. And lastly, you can ask for the full stack, which is the same as the stack which you see on the left, but which has all the anonymous intermediate parsers. So in FastParse, everything's a parser. So expression and side are parsers, but side tilde plus tilde side is a parser. Paren tilde expression tilde closed paren is a parser. These are all parsers. You did not give them names. But if you're trying to debug something that's behaving weirdly, this is very useful to be able to look at. Why would we do this? What are the use cases? If your parser is wrong, you can debug it very easily. So it is much easier to debug than 1,500 lines of while loops and if statements and mutable variables. If your users put something wrong into the input box that you are then parsing, you can tell the user you did something wrong, and you don't just tell them a syntax error at index 7. You can say syntax error index 7 because I was trying to parse a method definition index 4 because I was trying to parse a class definition index 2. So this is kind of much more detailed error reporting, which FastParse puts in effort to collect. So if you want to, you can put in effort to provide to your users rather than just bailing out with a random string. And lastly, you can customize the error messages much more. For example, if I know that every time something parses and fails, the user probably made some mistake. Not guaranteed, but like probably confident enough that I will want to tell the user. Well, I don't need to go back into the parser and put random code here to throw an exception with the string I want. Instead, I can just, after the fact, say, hey, failure, does your stack contain this parser? Like this is literally a parser object being compared to another parser object. This is not some string or some special syntax. Does your stack contain the parser foo.side? Yes? OK, here's a message. So that's the kind of thing that this is meant to be used for. So to demonstrate what kind of error messages this gives you in real code, here are some examples from a Scala parser. From the Scala parser I wrote versus the Scala parser that the Scala team has worked on for a long time. It's much faster than the FastParse version. So what's wrong with this syntax? Come on, no one knows what's wrong with this syntax? I need a new line? That's wrong. What's wrong with this syntax? I have two cases, and I need like an arrow or something in between the two cases in order to make it work. So scala-c says error expected but case found. FastParse says I expected either a pipe arrow or a Unicode arrow, and I found a case, which is comparable, except for the fact that in the FastParse Scala parser, I did not put any effort to try and collect this information. It's all done automatically. And it's arguably more correct, because you could have put a pipe here, and it would have continued parsing. Here's another case. var equals 2. What's wrong with this? I need a variable name. So scala-c says illegal start of simple pattern. OK? So I need to put something there, something that's simple and is a pattern. Not sure what. FastParse says I expected either a binding followed by infix pattern, or just the infix pattern itself, or I expected some kind of variable ID, but you gave me equals 2. So this is the kind of thing that in FastParse you get exactly for free a pretty reasonable error message. And it's not the perfect error message, but it's pretty close to what you can want. And if you want to, because all these are actually objects and not just strings, you can drill into them and show more things if you wish to. So debugging, the thing you do a lot with parsers when you're working on them is you're debugging them, because once you stop debugging them, they're done and you go home. So FastParse lets you use a .log method, which says whenever this parser gets tried and whenever it finishes success or failure, print something and let me see. So I'm going to log the side parser and I'm going to log the expression parser, because I know something's wrong with this, but I'm not sure what it's doing. Like, why is it misbehaving? I'm not sure. So this is what you get from adding those two log statements printed to your console. The stuff on the right is what you get. The stuff on the left isn't what you get, but you can derive it by looking at the parser and by looking at input text and counting characters. So if you want to, you could pretty print this better, but by default, you only are showed this stuff. But it's pretty detailed. You can see you try the expression, try the side, try the expression, try the side. This side finished from index 1, finished at index 2. Tries another side, index 3. Tries the expression, index 4. Tries the side, index 4. Succeeds at index 5. Tries one, index 6. Succeeds at index 7. The expression I tried earlier, index 4. Succeeds at index 7. The side I tried earlier, index 3, then fails at index 7. And you can see the failure propagating back out of the call stack. And this is the kind of thing that makes it really easy to debug parsers. It becomes a mechanical thing rather than an intellectual thing. Something's wrong, add logs. OK, one of these people seems to be misbehaving. Look at his children, add logs to them. Which one's not getting called at the correct time? OK, one of them is misbehaving, add logs. Eventually, you're at the point where something's obviously wrong, and you fix it, and then you move on. So while there's talk of debugging, the long and short of it is that you don't tend to spend time working with parsers that actually work. You tend to spend lots of time working with parsers which don't work. So once your parser's done, you are done. And so FastParse actually is optimized to give you a great experience when your parser is not working. And even for your users, when your users putting things into the input box on your website and wondering why it's not working, it sucks to have like syntax error at line 7 thrown at you. It's much better to say like, well, I expected a curly brace or a pipe or an equal sign, and you gave me an X. That's a much better experience for a user to get. Let's talk a bit about implementation details. So FastParse, like the scala-parser-combinators, is a straightforward recursive descent, for those of you who know what it is, a parsing expression grammar. So but what that means is that it tries, if in the case of, let's go back to example, in the case of something like this, it tries this, then it tries this, and if either of them fails, it backtracks out, and let's put a cut. In the case of something like a OR, it tries the thing on the left. If it fails and there's no cut, it will backtrack out and try the thing on the right. And if you have multiple ORs, it will then try from left to right, to right, to right, to right. And it's very simple and relatively predictable. So there are no fancy algorithms. There's no GLL. The worst case performance is always exponential with this kind of recursive descent parser. There's no fancy, like, if I have ambiguous grammar, let's disambiguate it, or let's keep all possible parsers and disambiguate it later. There's none of that. FastParse works basically mechanically. There's no asynchronous or push parsing. There's no XML SAX style event-based parsing. It doesn't parse late. It doesn't parse anything but a string. It's pretty simple to understand. And it doesn't do any sort of macro optimizations or parser-based transformations. Like what you write is what will execute in a very predictable way. It's as object-oriented as you can ask for. So everything is a parser plus T. You can implement your own parser plus T's. It has the parse function that you can implement, and it's really straightforward. Even though it's externally immutable, the insides of each parser T are optimized and very fast. That's what I showed you earlier. We use while loops inside. We use tail recursive functions. We use pattern matching. We don't use lambdas. We use bit sets instead of normal sets because they're faster. And all this, together with mutable failures and successes inside the parser, are what helped it make it 85 times faster than scala-parser-combinators. So what have I used FastParse for? So on the example on the website, on the documentation page, FastParse also compiles to Scala.js, so you can write parsers that run in the browser. Like you can see that here's an arithmetic parser, which is a bit more complete. It does precedence, it does plus minus times divide, and it actually evaluates all of them separately. So you can see if I do like 1 plus 2 plus 3 plus 4 paren times 17, you get a reasonable answer. If I mess it up, you can see that, oh, you gave me a closed paren. I expected a number or parens, like a set of parens with stuff inside. Parens being this fella. There is an example of a Whitespace insensitive parser, which FastParse supports out of the box. So you can put as many spaces in your parser as you want in certain places, and it will ignore them. Here you can see we are customizing a space to mean anything which is a blank space repeated 0 or more times. Indentation-based grammars. So FastParse lets you very easily parse things like this. 1 times 4, 7. And it does this in a honestly pretty remarkably simple way. So the parser is parameterized based on how much the indentation it can parse. And when I want to parse an indented block that's further indented, I simply instantiate a new parser and find out how much deeper it has to be and use the mount deeper to instantiate my new parser and start parsing from there. So you don't need any like Lexer hack. You don't need any preprocessor to inject synthetic tokens into your token stream like if you had a Lexer parser traditional way of doing it. You just have this nice recursive parser which can instantiate itself. And you're done. You can parse arbitrary whitespace indented code or syntax, YAML. There's a JSON parser, a pretty complete one that is what I use for the benchmark. And there's maybe like 30 lines of code total, 40 lines of code. And it runs pretty fast. And it parses the AST, which I defined down here. This shows most of the details what you need to care about when writing parsers. For example, here's how you parse Unicode escapes. Here is how you parse an array, which is a square bracket followed by a JSON expression, more than one, separated by commas, followed by a space, followed by a closed square bracket. This then gives me a sequence of JS values because JSON expression parses a JS.value, so .rep gives me a sequence unconverted into a JS.array. So I need to map it using this. That's a slightly more real-world parser. There's a Python parser which I wrote recently, which, before we talk about Python parser, we can take a moment to look at the error messages the JSON parser gives you. So I remove this quote from the start of an object key, a dictionary key, and it says, I found 4 numbers, quote, colon, I expected a quote. And again, this is basically for free. I did not have any error reporting code in this except for putting cuts in a few relevant places. There's a Python parser, which is another example of a whitespace-sensitive parser, indentation-sensitive parser. So you can see that we do a similar trick where, let's make this bigger, where the thing which contains all the parsers for statements is itself parameterized based on how indented it is. So if I want to parse something that's deeper, I have a parser which looks ahead to find how many more, what the next indent level is, and then I simply flat map it and instantiate a new set of parsers with that indent level and go from there. So it's very straightforward. And then I have the last one to show off here is the scala-parser, which you can see the error messages it shows off. So here I found end of input, expected a close comment. Here I found curly new line. I expected some kind of either backtick ID or a plain ID. And this is all, in the Scala parser's case, it's written about 700 lines of parser-combinated code. And that is used for a markup language I wrote, which is what I use to write all this documentation, which basically looks like that. So in my opinion, parsing text isn't that hard once you have proper tools for it. Like parser combinators are great. In fact, they're very, very good, except that they are incredibly, incredibly slow. And then the Spray people went and made Parboil 2, which is very, very fast, but then has crazy, crazy error messages. And I thought, well, it can't be that hard. If the Spray people could make it fast and the Scala people could make it convenient and have good error messages, why can't we have something that's fast and have good error messages? And it turns out you just need to replace a bunch of monads with while loops, and you get something that's both convenient, fast, flexible, and has great errors and a pretty pleasant API. So I have 10 minutes budgeted for demo, so let's do the demo. Does anyone want to suggest a language that's not JSON they want me to parse? Any language?
Haskell.
Haskell, okay, let's try parsing Haskell. How do you parse Haskell? So here's a hello world project. Big. Okay. So here you can see you have a library dependency on FastParse. Make it a bit bigger. Let's go to my main method. So currently it's just printing hello world. How do you parse Haskell? I don't actually know how to parse Haskell. I think you have something like let, is that right? So let's try doing that. Val let equals a parser of let. And then I need to import fastparse.all, and then let's write some unit tests. So printline let.parse let, and let's printline let.parse blarg. Okay, so I've parsed lets. What do you put after lets in Haskell? You know Haskell.
Yeah, sure. So you need a variable name?
Okay, let's do variable name. So a variable name is a parser.
Identifier, not a variable.
Okay, identifier is a parser which has, I guess, has some kind of alphanumeric. So let's stick with alphanumerics for now and do operators later if you have time. So I guess A to Z, A to Z. This A to Z syntax isn't particular to FastParse. Sorry, let's make this bigger. This A to Z syntax isn't particular to FastParse. It's just a normal like character range. And then, I don't know, do you use underscores in Haskell? Maybe, I don't know Haskell.
Also primes.
Okay, primes, let's do that. Let's also build some kind of syntax tree. So I'm going to have a let is going to have some kind of variable name. Can I have more than one variable name? No, okay, let's do that. So val, let's do a let is equal to a let followed by, I'm just going to call this white space. So more than one white space for now. Who cares about new lines? Followed by white space, followed by identifier. Okay, what's wrong with identifier? Wrong forward reference. So I probably need to move this into the object body and then I'll stop complaining. Okay, so I run it. You can see that the parse is failing because it expected a character in A to Z underscore a prime at index 3. Instead, it found the end of input. So I'm going to call it let foo. And now it's going to parse nothing because I didn't capture anything. So let's capture the identifier with a bang. Now it prints a success F. That's probably not right. Oh, because I forgot to say it is more than one character. So, so as you can see, I'm only parsing, it's only parsing until index 5, which is 1, 2, 3, 4, 5. So that's clearly not right. So one thing you can do to make it parse to the end is to make it parse to the end. And then you'll say, I expected the end of input, I still found like 2 O's. What are those doing there? So now I can say, well, identifier needs more than one character. So let's do that. Okay, now it's succeeding parsing foo. And let's map this into let. So now you can see that identifier is okay, you can't see because IntelliJ doesn't scroll it up. But identifier is a parser of main dot let, and type checks you get a let with a foo inside. Okay, what else does Haskell have?
So
you have an equals, right?
Your let, yeah, it needs an equal.
Okay.
And a statement equivalent to or expression. Sorry.
And then I need an expression. Are you looking up on your phone?
No.
Okay, so what goes in? Okay, so here I'm going to have a dummy parser for expression. Okay, let's foo equals.
So like let foo equals expression in some other set of expressions.
Okay, so expression followed by in, followed by what? So it has to be recursive, right? I can put another let in there.
You could, or you can do like let A equal whatever, B equal whatever in C.
Okay, so let's just do the recursive case first. So let whitespace identifier. I need to put a whitespace here. So I'm going to get tired of doing all this whitespace handling soon. So I'm going to use FastParse's whitespace API. So what this does is I'm going to say a whitespace is anything which is more than one space. Maybe it needs new lines, who knows, I'll figure that out later. And then I'll import fastparse.noAPI, and I'll import fastparse.whitespace-api.all. And that should make it compile. Oops, what's wrong? OK, it is not FastParse, it's my own, I defined it up here. OK, so failure. So I need to have some kind of expression. I'm just going to call my expression like foo for now. We can figure that out later. That's not right. My expression. FastParse, let's let foo equals my expression in. And presumably, I need some kind of expression node. So what can an expression node be? So let's do that. And then, OK, so presumably, I want to be able to have some kind of expression in the syntax tree. So let's do that. And a let must have, for now, let's just say, let some identifier bound, which is going to be an expression, and let's call it like returned or something, which is an expression. So now I'm identifier. I don't want to map my identifier to a let because identifier shouldn't return a let. It should just return a string, which it now does. If you look at this, you can see the tiny, tiny text. And then I'm going to say, well, the expression must capture something. I'm going to say I don't care what it captures. It's going to be an expression, AST. And I'm going to map this into case ident. Let's call this left-hand side and right-hand side. Goes to let ident left-hand side, right-hand side. OK, so now I have this thing parsing nothing. So let's try and make some more interesting expressions. I guess an expression, let's say an expression can be dummy expression. So let's say this is the only expression you can ever have in Haskell other than a let. So an expression is going to be a dummy expression or a let. What's wrong? So recursive value needs type. OK, so compiler's complaining. So I'm going to annotate this as a parser of an arbitrary expression. Now it's OK. So now we can parse let foo in my expression. I can also parse. Let's make Whitespace eat up new lines because this is getting very annoying. So come on, format, let foo go my expression. Let foo equals my expression in my expression. OK, failure. Let's see if we can figure out why it failed. So it's complaining that, well, after.
Considering let an expression, right? Is that your problem?
Well, over here, I'm saying that an expression is a dummy expression or a let, and a let is followed by two expressions. So that should be correct. So let's try logging it, see what happens. OK, so it's trying to parse a let at index 0. That's over here. It then fails because it tried to parse identifier index 3. That's over here. That seems fine. It then tried to parse a character in 0 to something. So let's log the identifiers to see what's happening. I think can't really make out. So it tries to parse an identifier index 3, and it fails. So let's try to log the char in itself. And to make our thing simple, I'm just going to like remove uppercase characters for now because making my logs annoying to read. So it tried to parse a char in at index 3. OK, so here's my mistake. Over here, I said this means that a white space is anything which is a space followed by a new line at least once. So that's clearly wrong. So this needs to be character in a space or a new line. And let's remove the logging because it's really verbose and getting hard to read. And get rid of this logging too. Okay, we're in business, so I'm parsing two expressions. Equivalently to this char in, I could also use, if I wish to, I could also use something like this, like a whitespace or a new line. It's equivalent, it also parses. Okay, so clearly an expression can't just be a constant thing. Expression must be a trait. Expression, let's make it sealed. And then let extend expression. And let's make another case object. Let's make a case class. Dummy expression extends expression. Do I have case? Whoops, case class, there we go. Okay, so let's make the compiler happy. What's wrong here? Plural. What's wrong here? This needs to be dummy. This still needs to be the arbitrary expression. This returns a let, which is correct. Okay, so I have a let of a foo of a dummy expression and dummy expression. So that doesn't seem right, but let's see why this is not right. So the problem here is that in this arbitrary expression, this let here, you can't see it, but this is a parser of let. But when I capture and then map it, I'm discarding the let that it returns, and I'm replacing it with a fixed dummy expression. So that's clearly wrong, and that's because this map to dummy expression should be on the dummy expression rule, because that's the one that returns a dummy expression. The let parser just returns a let. Okay, so that gives me a let of foo of dummy expression and a let of foo of dummy expression. Okay, so what else does Haskell have? What does the where statement look like? It's something.
At the end of an expression, it is basically like a let, except there's no like the end. It's just a way to define extra things at the end.
Oh, okay, so a where is equal to a.
It's actually doing really well.
Okay, so what do I put after a where?
So the where goes at the end of an expression.
It's something like where x equals something, right?
Yeah, where x equals.
Okay, so a where is followed by expression, followed by a equals, followed by another expression, and then so.
There's only one where for now.
we can do multiple. It shouldn't be hard, but let's start off with wheres. It only goes at the end of a let or at the end of any expression. Okay, any expression. So let's make that its own AST node. Where, so it takes the expression, and it has a, let's assume it just has one. So we'll have a bound, which is a ident, and name like thing, which is an expression. That's like totally wrong. Bound, which is a string, and name, which is an expression. Okay, so so at the end of any expression can be a where clause. Wrong. Why is it wrong? Okay, so I'm telling it after this there's a where clause. The problem is that now this doesn't just return an expression, it returns expression, and where itself is a parser of two expressions. So what I want to do here is, let me see if I can figure this out. I'm going to make the where clause optional for now, so that should at least make the existing thing parse. And I'm going to map this to say case. Let's call this left-hand side. None goes to left-hand side. And I know this is going to crash if I put in a where, but whatever. Okay, so that looks like it's still parsing the correct thing. We're back into at least something works mode, where my expression equals my expression. Okay, so now that's going to blow up with a match error because I didn't handle this case. So let's just do like some. I don't know what is in here. Let's ask the compiler what's in here. Hey, IntelliJ, what's in here? Is a tuple of expressions. So it's. I'm quite sure this should. Let's say this is an identifier for now. I'm quite sure you can't have an arbitrary expression. So this is going to be ident expression is going to be a where left-hand side. I called it bound for some reason, and expression. Okay, why is it complaining? Expected string actually main.expression? So you can see here it's also complaining that it actually is a parser of tuple of string and main.expression, but here I annotated it as 2 expressions, so that's wrong. So if I make this string, that should shut up and that should work. Where, so the problem is that I forgot to make where extend expression, extends expression. Okay, and it works. And let's try another thing. Let foo equals my expression where my expression equals my expression in let foo equals my expression. Okay, so that's it for the live coding. I'm not going to do any more. Cool, so yeah, I don't know Haskell, so whatever. So I'll take questions.
What was the argument to rep? One you were giving?
So where is my dot rep? Here it is. Dot rep takes a minimum number of iterations. So I could say I need to rep 0, which is default, which means that 0 or more. I could do 1 or more. And it also takes optional separator, which is what we use just now for JSON. So you have a comma or something in between. You can use that. Any other questions?
Are there any implicit converters or implicit context ported when you report a FastParse at all?
Yes. So every operator is an extension method. And the reason for that is that you may want different sets of operators at different times. For example, here I want a white space aware set of operators. And here I want a non-white space aware set of operators. Remember, the white space itself can be arbitrarily complex, may have comments and stuff inside. So that means that all of these are provided by an implicit, which is provided by this implicit here. And apart from that, there is one more set of implicits, which is used to do the turning things into tuples. So if you look at, if that's, okay, why is it complaining? Did I break it? No, I didn't break it. So if I do something like val x equals a parser of string capture, val b equals a parser of that, val c equals a parser of that, val d equals a parser of that, and do val e equals parser of a followed by b. It should be a small a. So you can't, so this is a parser of string. You see compiles. If I make it fall to C, it then says it's a parser of string. And if I make C return unit, it then becomes string again. So there's a bit of implicit magic that it does to make the tuples longer. So that's maybe confusing in some cases, but I try to keep it minimal.
So you don't have unit in the tuples, that's awesome.
Sorry?
You don't have tuples of string, unit, string.
Yeah, I don't have tuples of string, unit, string, and the thing which creates a new tuple, if the thing is a unit that's being not added, it will not do anything, which is great because it doesn't allocate any memory. So over there.
So I thought I saw a few days ago that this was submitted with FastParse.
Yeah. Sure. Honestly, I have no clue. As far as I can tell, nobody involved in that discussion except me has ever used this library. So there are a bunch of people who have used the library, like in the Scala.js community, people use it a reasonable amount. But there are a lot of people saying that, we should use FastParse. Everyone's like, hey, is it actually better? And some other guy's like, I don't know, someone should go find out if it's better. And a third person says that it might be better, someone should try it, and no one's actually trying it. So at some point, when someone actually tries it, maybe it stands a chance. But for now, as far as I can tell, it's all talk. Any other questions? Going once, going twice, you look hesitant.
I have to remember what it was.
Okay, well, you look like you had your hand up.
Can you parse streams at all?
You cannot parse streams. There is a pull request open that would make it able to parse streams, but I haven't accepted it because it makes performance a lot worse. And we haven't quite figured out how to make that work generically well while keeping performance good. Yeah. Okay, yeah.
I think in one early slide you had tilde and like right
The arrow. It looked like an arrow, right?
yeah.
Yeah, this was a parser combinators.
Oh, that wasn't the
Yeah, so in parser combinators, this arrow says that parse open paren followed by expression, but ignore the value of open paren. And similarly for the arrow in the other direction means ignore the thing on the right. And FastParse doesn't need this because by default we just ignore everything and only you have to say dot exclamation mark if you actually want something. Cool, anything else? Going once, going twice, yeah?
Is there anything to like detect an infinite loop, like if you make something left recursive?
There is not. So for example, if I do, let's delete my beautiful Haskell parser because it's, and I deleted the main method too, that's silly of me. So if I say like, if I say A equals B and B equals A, and I try to do a.parse like blarg, let's just do A for now. Recursive value needs type. Okay, so this is a parser of string. This is a parser of string. And then like, it just like blows your stack. So I haven't thought of a clever way to make it actually detect it. I'm sure it's possible, but I don't know. Okay.
So if you have something that's like 1,000 levels deep in the Stack Overflow, right?
Yes.
I bet trampolines would make it much slower.
Probably, yeah. And like, if you have something that's 1,000 levels deep, like it's quite possible that your programmer will have a Stack Overflow trying to parse it in his head. Like, what's going on? Yeah, like you probably shouldn't. You can, but like, yeah. So like, I explicitly didn't want to do any fancy runtime, so there's no like asynchronousness or trampolines and stuff because that really slows it down by a lot. And in most cases, like I'm defining most cases as my cases, but in most cases you probably don't need them. Okay, anything else? Going once, going twice, gone. Okay, thanks.